A solution for summer drought in cold climates by 1715 C.
Winter in New England feels never-ending. We wished for hot summer days and remembered
what our yards look like in July. Brown, dry, and dusty. Not a fun place to play.
The snow is melting and the water is coming down the driveway into a drain. What if we could harness all this snow from the winter and use it during the summer during droughts? Wouldn't that be great?
Riley told us she went sledding down Olympia, the giant snow woman in Bethel, Maine. Olympia did not melt until the end of July. Olympia had an older brother, Angus, who didn't melt completely until the end of June, so we knew we might just have an idea that could work. Our team researched to see if anyone had built a snow structure to save water for the summer.
We found our answer in the Himalayan desert, where they are solving a real drought problem by making artificial glaciers called ice stupas to save water for the spring.
We set up an experiment where we had equal amounts of loose snow and snow made into a snowman. We wanted to see how much longer a snowman would last at room temperature than loose snow. The loose snow melted in 5.5 hours, and the snowman took 14.5 hours. With all the information we collected, we now knew
shape slows down the melting process. We know through observation and experimentation that snow can be stored to last into the summer in the form of a snow person.
We wanted to find out how much snow we needed to have water through July. We found the snow melt equation from the USDA. Melt rate equals coefficient times degree days, but we needed to determine the coefficient for a snow person. We made our calculations based on information from Olympia and Angus, as well as historical temperatures collected from the NOAA.
We took the average of Olympia's and Angus's pounds per degree days and got 4,500 as C.
Now we need to find the degree days. To do that, we took the data from the Worcester Airport, which is at 1,000 feet, and Hopkinton is only at 450 feet. So we used the altitude difference formula from a Canadian website.
The formula is the temperature in Celsius plus 1.1.
Because the website was from Canada and it was in the metric system, but the data from the NOAA is using the imperial system, we needed to convert.
At the end, using the formulas, we found out that we needed a snow person who weighs about 17 million pounds.
According to the Weather Channel, the most appealing snow person has a 3-to-1 ratio. To find the amount of snow per snowball, we calculated the volume of each snowball using a 3-to-1 ratio and the formula for the volume of a sphere.
The smallest ball is 500,000 pounds, and the largest is 27 times bigger.
The Weather Channel said 31 degrees is the best temperature for a snowball, which we didn't have. But we still tried. Like Stoneham, we used gravity as our power source. We didn't make a 12 million pound snowball. We decided it was time to build an assembly line, but all we had was small plastic parts. But that didn't stop us from starting a prototype to build a snowball, then roll it down a mountain. How do you roll a snowball up a mountain?
We decided to visit Shoemaker Equipment in Belmont, New Hampshire, where we were able to get some advice from Mr. Shoemaker, who designs and builds lots of assembly systems. I asked him if he had any ideas about moving something that is super heavy, like a huge snowball that weighs about 12 million pounds, which we calculated earlier. He said water is a good way to move something heavy like your snowball.
That gave us the idea we needed to finish our giant snowball making machine. Could something like this be done in California to reduce drought and help prevent wildfires?